Our Sun, a blazing ball of plasma, is far from a tranquil neighbor. These events, known as solar flares and coronal mass ejections, are a stark reminder of the Sun's raw power, capable of disrupting our technological infrastructure and painting the sky with breathtaking auroras. Every 11 years, our Sun reaches a peak in this cycle, a period we call the solar maximum. The year 2025 is projected to be the next solar maximum, a time when our Sun will once again flex its magnetic muscles. Understanding and preparing for the solar maximum is not just an academic exercise. It is a matter of safeguarding our technological civilization. The Sun, a giant ball of hot, ionized gas called plasma, is in constant motion. This motion is driven by the intense heat generated by nuclear fusion in its core, where hydrogen atoms are fused into helium, releasing enormous amounts of energy. The Sun's rotation, however, is not uniform. The equator spins faster than the poles, and this differential rotation has profound effects on the Sun's magnetic field. Over time, these magnetic field lines become so distorted and entangled that they break through the Sun's surface, forming sunspots. The number of sunspots visible on the Sun's surface is a key indicator of solar activity. During solar minimum, the Sun may have few or no sunspots for days or even weeks at a time. This cycle of increasing and decreasing solar activity, marked by the rise and fall of sunspot numbers, is known as the solar cycle. Solar maximum is not a single event, but rather a period of heightened solar activity that can last for several years. During this time, the Sun's magnetic field is at its most dynamic, leading to a significant increase in the frequency and intensity of solar flares and coronal mass ejections. Solar flares are sudden, intense bursts of radiation from the Sun's surface, often associated with sunspot groups. While the Earth's atmosphere protects us from the most harmful effects of this radiation, it can still disrupt radio communications, GPS signals, and other technological systems. Coronal mass ejections, CMEs, on the other hand, are massive eruptions of plasma and magnetic field from the Sun's corona, the outermost layer of its atmosphere. Understanding the nature and potential impacts of solar maximum is crucial for mitigating the risks it poses to our technology-dependent society. The Earth is constantly bombarded by a stream of charged particles from the Sun, known as the solar wind. During solar maximum, the frequency and intensity of solar storms, such as solar flares and coronal mass ejections, increase significantly, leading to more frequent and intense geomagnetic storms on Earth. One of the most visible effects of geomagnetic storms is the aurora borealis and aurora australis, also known as the northern and southern lights. These spectacular displays of light and color occur when charged particles from the Sun interact with atoms in Earth's upper atmosphere, exciting them and causing them to emit light. However, geomagnetic storms can also have disruptive and potentially damaging effects on our technological systems. The intense radiation from solar flares can ionize Earth's upper atmosphere, interfering with radio communications, GPS signals, and other forms of radio-based navigation. The charged particles from coronal mass ejections can also induce electric currents in power grids, potentially overloading transformers and causing widespread blackouts. As our reliance on technology increases, the potential impacts of geomagnetic storms become even more significant. As we approach the next solar maximum, predicted to peak in 2025, it is more important than ever to prepare for the potential impacts of increased solar activity. Space weather forecasting is crucial for providing timely warnings of solar storms, allowing us to take steps to mitigate their impacts. Space weather forecasters use a variety of instruments, both on the ground and in space, to monitor the Sun's activity and track solar storms as they travel through space. Hardening our technological infrastructure against the effects of geomagnetic storms is another crucial aspect of preparation. This includes designing power grids that are less susceptible to geomagnetically induced currents and developing radiation-hardened satellites. Public awareness is also essential for building a resilient society capable of weathering the storms, both literally and figuratively. In an era increasingly reliant on technology, understanding and mitigating the risks posed by space weather is no longer a luxury, it is a necessity. Space-based observatories like NASA's Parker Solar Probe and ESA's Solar Orbiter are providing unprecedented insights into the sun's behavior, allowing scientists to study the mechanisms driving solar activity in greater detail. These missions are helping us to unlock the secrets of the sun's magnetic field, understand how solar flares and coronal mass ejections are generated, and improve our ability to predict these events. On the ground, scientists are developing increasingly sophisticated computer models to simulate the sun's behavior and predict the impacts of solar storms on Earth. The study of space weather reminds us that we are not isolated on Earth, but are part of a vast and dynamic solar system, subject to the whims of our nearest star. Science will continue to be our guide and protector as we navigate the challenges and opportunities of the cosmos.